Welcome back. In this video, we're going to look at examples of using the limit comparison test for series. Let's get to it. All right, so here's our first example. We want to use the limit comparison test to determine if the series converges or diverges. All right, and so here we have our series, the sum from n equals 1 to infinity of 1 divided by 2n squared minus 3n plus 4. All right, and so as a reminder, the limit comparison test says this. If we have a sequence a sub n greater than 0 and a second sequence b sub n greater than 0, meaning both sequences are positive, and the limit as n approaches infinity of the first sequence divided by the second sequence is equal to L, and L is a finite and positive limit, then we can conclude that the series for a sub n and the series for b sub n both converge or diverge. All right, and so what that looks like for us when we want to determine the convergence of a series is we will start with a series a sub n, and we're going to choose a series to compare it to b sub n, and that should be a series that we do know the convergence of, whether it converges or diverges. And then we want to take the limit as n approaches infinity of a sub n divided by b sub n, and if we can show that that limit is finite, then we can conclude that our original series a sub n will have the same convergence as b sub n. All right, so if we go back to our example, we need to choose a series that we can compare to this series for the limit comparison test. And typically we're going to be comparing to a p-series or geometric series that we can easily determine the convergence of. And so when you have an algebraic series like we have here, where it's just made up of powers of n in the numerator, denominator, or both, typically we will compare this to a p-series that we will form by looking at the highest power of n in the numerator and denominator. All right, so in this case, our series will be the sum from n equals 1 to infinity of 1 divided by n squared. This is the p-series that we will compare to this series because the highest power of n in the numerator is 0. There's no n's up here, so we're just going to use 1 as our numerator. And in the denominator, the highest power of n is n squared. So we have n squared in our denominator here. And so this series right here is the p-series that we are going to compare to our original series via the limit comparison test. And this is a p-series because we have 1 divided by n raised to a power. In this case, that power is 2. And so for this p-series, p is equal to 2. And since that is greater than 1, we know that this p-series is going to converge, right? When the value of p is greater than 1, it will converge, but if it's less than or equal to 1, then it will diverge instead. All right, so in this case, our p-series converges because 2 is greater than 1. All right, so now that we have our comparison series and we know that it converges, we are now ready to look at the limit of this series divided by this series. And so here's what that looks like. We'll have the limit as n approaches infinity of 1 divided by 2n squared minus 3n plus 4 divided by 1 divided by n squared. All right, so we have the expression from our original series and divided it by the expression from our comparison series. Now in this case, we're dividing by a fraction, and so that's the same as multiplying by the reciprocal of that fraction. And so instead of dividing by 1 divided by n squared, let's multiply by n squared divided by 1. And so if we simplify, this is equal to the limit as n approaches infinity of n squared divided by 2n squared minus 3n plus 4. All right, and so now we have a limit that we can evaluate. In fact, this should be a very familiar type of limit where n is approaching infinity. And so when you have a limit as n approaches infinity of a rational expression, a quick shortcut that you can use is look at the highest power of n in the numerator and denominator, and if they are equal, that limit is just going to be equal to the coefficients of those terms divided by each other. So in this case, note that we have n squared in the numerator, and in the denominator, the highest power of n that we can see is also n squared, right? We have 4, which doesn't have an n, and then we have 3 times n to the first power, and then we have n squared. And so the coefficients of our n squared terms are 1 and 2, and so this limit will be equal to 1 divided by 2, or 1/2. Okay, so that's a shortcut that maybe you are familiar with, maybe you're not, but you can use that for a limit as n approaches infinity of a rational expression. All right, but now we have shown that this limit is equal to a finite value. And so we can conclude that our original series will also converge just like our comparison series. All right, and so our final answer is that since the comparison series, the sum from n equals 1 to infinity of 1 divided by n squared converges, the original series, the sum from n equals 1 to infinity of 1 divided by 2n squared minus 3n plus 4, must also converge. All right, so that is the result of the limit comparison test for this example. Let's look at another example. All right, so next up we have this series, the sum from n equals 1 to infinity of 2 plus 2 to the power of n divided by 3 plus 3 to the power of n, and we want to use the limit comparison test to determine if it converges or diverges. All right, and so the first step is to find a series that we can compare to this series, specifically a series that we do know the convergence of. So typically that's going to be either a p-series or a geometric series. In this case, I'm leaning towards using a geometric series because I see that we have 2 to the power of n and 3 to the power of n within our series. And so that is really close to the geometric series where we have the sum from n equals 1 to infinity of 2 to the power of n divided by 3 to the power of n, which can be rewritten to be the sum from n equals 1 to infinity of 2/3 to the power of n. Right, when both the numerator and denominator are raised to the same power, you can just take that whole fraction to that power. And this is in the form of a geometric series. We have some value raised to the power of n, and that value is known as the common ratio r. And in this case, r is equal to 2/3. And when the common ratio is less than 1, like it is here, we know that our geometric series converges. If it was instead greater or equal to 1, then the geometric series would diverge. All right, and so now we have a comparison series for our original series. You can see that they are similar, but they are different series. We do have this extra 2 and 3 in the numerator and denominator. And so now that we have that comparison series and know that it converges, we can look at the limit of this expression divided by this expression, right? The original series divided by the comparison series. So we will have the limit as n approaches infinity of 2 plus 2 to the power of n divided by 3 plus 3 to the power of n divided by 2 to the power of n divided by 3 to the power of n. All right, now remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so instead of dividing by 2 to the power of n divided by 3 to the power of n, what we can do is flip the numerator and denominator and just multiply by that instead. So we will multiply by 3 to the power of n divided by 2 to the power of n. That is the reciprocal of this expression. All right, now if we simplify, this will be equal to the limit as n approaches infinity of 2 times 3 to the power of n plus 2 to the power of n times 3 to the power of n divided by 3 times 2 to the power of n plus 3 to the power of n times 2 to the power of n. All right, so I just multiplied 3 to the power of n to both of these terms to get this numerator and multiplied 2 to the power of n by each of these terms to get this denominator. And now we can simplify this a little bit. Since 2 and 3 are both raised to a power of n, we can actually multiply those bases. So 2 times 3 is 6. So this is actually 6 to the power of n, and 3 to the power of n times 2 to the power of n will also be 6 to the power of n. And so I'm just going to simplify that right now. We're just going to have 6 to the power of n as that term in the numerator and denominator. And now how can we evaluate this limit from this point on? Well, a common technique that you can use to simplify a limit like this is to multiply by a form of 1 that will make things simpler. In this case, what we're going to multiply by is 1 divided by 6 to the power of n divided by itself. And what that's going to do is make each of these terms just 1, because 6 to the power of n divided by itself will be 1. And then this is going to simplify nicely with this 3 to the power of n, and this is going to simplify nicely with this 2 to the power of n. And so let me show you what that looks like. If we simplify, this is equal to the limit as n approaches infinity of 2 times 3 to the power of n divided by 6 to the power of n plus 1 divided by 3 times 2 to the power of n divided by 6 to the power of n plus 1. All right, so 6 to the power of n divided by itself is 1. That occurs in the numerator and denominator, so we have those 2 plus 1s. And now we have 3 to the power of n divided by 6 to the power of n, and then 2 to the power of n divided by 6 to the power of n. Okay, and so now what we can do is simplify these two fractions. Since they're both raised to the same power of n, the numerator and denominator in both fractions, we can just divide those bases. So 3 divided by 6 is equal to 1/2. So we would have 1/2 to the power of n. So I'm just going to rewrite that to be 1/2 to the power of n. And 2 divided by 6 is 1/3. So this is just going to be 1/3 to the power of n. So we'll have 1/3 to the power of n. And then we can rewrite them even further, because if we take the numerator and denominator to the power of n, 1 to the power of n is just 1. So this would actually be the same as 1 divided by 2 to the power of n. And the same will apply down here. We'll have 1 to the power of n and 3 to the power of n. And so we're just going to have 1 divided by 3 to the power of n. And so I will write that right there. Okay? And so now if we look at this expression as n approaches infinity, we only have 2 n's to look at here. And as n approaches infinity for this expression, the power of 2 is increasing. And so this denominator is going to get bigger and bigger. And so we have a fixed value divided by an increasing value. And so that is going to approach 0. So we have 2 times 0, which is 0 plus 1. So our numerator is equal to 1. And then in the denominator, we have 3 times 1 divided by 3 to the power of n. This is very similar to what we have up here. As n approaches infinity, this 3 to the power of n is going to get larger and larger. And so 1 divided by an increasing value is going to approach 0. So we have 3 times 0, which is 0, plus 1. And so our denominator is just 1. And so this limit is equal to 1. And so now we have found that this limit is equal to a finite value of 1. And so we can conclude that our original series will converge just like our comparison series. Okay? And so if I clean up my work here, our final answer is that since the comparison series, the sum from n equals 1 to infinity of 2 to the power of n divided by 3 to the power of n converges, then the original series, the sum from n equals 1 to infinity of 2 plus 2 to the power of n divided by 3 plus 3 to the power of n must also converge. All right, so that is our final answer that we can conclude based on the limit comparison test. All right, so here's our next example. Once again, we want to use the limit comparison test to determine if our series converges or diverges. And this time our series is the sum from n equals 2 to infinity of n cubed minus 1 divided by n squared plus 1 quantity squared. All right, so now the first step of the limit comparison test is to choose a series to compare to this series. And so in this case, I notice right away that we have a rational expression where we have n raised to a power. All right, so when you see that, that should tell you that you probably want to compare your series to a p-series of some kind. And you will find that p-series by looking at the highest power of n in the numerator and denominator. All right, now be careful. In this case, the denominator has a quantity that is being squared, and so the highest power in the denominator is not n squared. It's actually going to be n to the 4th power if we were to expand this denominator. And so that's what I want to do first here. I'm going to rewrite this series to be the sum from n equals 2 to infinity of n cubed minus 1 divided by this denominator expanded. So if we want to square this quantity, I'm going to use a little trick here. We're going to start by squaring the first term. N squared multiplied by itself is n to the 4th power. Then for the middle term, we're going to multiply these two terms together and then multiply them by 2. So n squared times 1 is n squared times 2 will be positive 2n squared. And then our last term of the expansion will be the second term squared. So 1 squared is 1, so we'll add 1. All right, and so this is another way that this series could be expressed. Now we can explicitly see what our highest powers of n are in the numerator and denominator. And so the comparison series that we are going to want to use is much easier to see. In this case, we will use the series where we have the sum from n equals 2 to infinity of n cubed divided by n to the fourth power, right? Those are the highest powers of n in the numerator and denominator. There is no higher power than n cubed up top, and there is no higher power than n to the fourth in the bottom. All right, now if we simplify this expression, we can divide n cubed out of the numerator and denominator, and so that will make this power of n 0 and this power of n 1. And so our series will actually be equal to the sum from n equals 2 to infinity of 1 divided by n, right? N to the power of 0 is 1, and n to the first power is just n. And so this series right here is a p-series. In fact, it's a special type of p-series where p is equal to 1. That is known as the harmonic series. And the harmonic series is a divergent series. When p is equal to 1 for a p-series, it is divergent. All right, so this series diverges. Okay, so keeping that in mind, now we have our comparison series. And so now let's take a look at the limit as n approaches infinity of this expression divided by this expression. Now I'm going to take a little shortcut here. Remember that dividing by this fraction will be the same as multiplying by its reciprocal. So we're going to have n cubed minus 1 divided by n to the fourth plus 2n squared plus 1 multiplied by n divided by 1. That is the same as dividing by 1 divided by n. Okay? Now if we simplify, n times n cubed will be n to the fourth power, and n times negative 1 is negative n. So I'm just going to erase this and rewrite the numerator. We will have n to the fourth power minus n, and now we have a limit that we can solve. Now, similar to our first example, we have a limit as n approaches infinity of a rational expression where n is being raised to a power in the numerator and denominator. And so when the highest power of n in the numerator and denominator is equal, like it is here, right? We have n to the fourth and n to the fourth. That limit as n approaches infinity will just be equal to the coefficients of those two terms divided by each other. So in this case, that will be 1 divided by 1. All right, so that is the shortcut to solving this limit. Because the highest powers of n are equal, they're both 4, the ratio of their coefficients will be the solution to that limit. And so this limit is equal to 1. Okay, and so since this limit is equal to a finite value, we can conclude that our original series will diverge just like our comparison series. And so that's our final answer. We can say that since our comparison series, the sum from n equals 2 to infinity of 1 divided by n diverges, that our original series, the sum from n equals 2 to infinity of n cubed minus 1 divided by n squared plus 1 squared, must also diverge. Okay, that is the final answer to this example. All right, so here's our next example. We once again want to use the limit comparison test to determine if the series converges or diverges. So in this case, our series is the sum from n equals 1 to infinity of 4n squared plus 5n divided by the square root of 10 plus n to the fifth power. Now, similar to our last example, we have a rational algebraic expression. And so if we look at the highest powers of n in the numerator and denominator, that's what we should use for our comparison series. So our comparison series in this case will look like this. We'll have the sum from n equals 1 to infinity of the highest power in the numerator, which is n squared. So we will have n squared divided by the highest power in the denominator. Now be careful here. You might be tempted to say that it's n to the fifth power, but that would be wrong. We also have this square root here that is affecting that n to the fifth power. So the actual highest power in the denominator is the square root of n to the fifth power. All right, remember that a square root is the same as taking the value to the 1/2 power, so we need to take that square root into account. In fact, we would say that this is equal to the sum from n equals 1 to infinity of n squared divided by n to the fifth power to the 1/2 power, right? We're taking the square root of n to the fifth power, so n to the fifth power to the 1/2 power would be the same thing. Now we could simplify this by multiplying those exponents, right? When you have a value raised to a power and that whole thing is raised to a power, you can simplify by multiplying the exponents. And so in this case, 5 times 1/2 is 5 halves, So our denominator will be n to the 5/2 power. So we have n to the 5/2 power. All right, so now if we simplify further, because this series right here, our comparison series, isn't currently in a form where we can easily decide if it converges or not, and so if I move this n to the 2nd power to the denominator to make that exponent negative, this will be equal to the sum from n equals 1 to infinity of 1 divided by n to the 5/2 power times n to the negative 2nd power. Now, n to the 5/2 power times n to the negative 2nd power can be simplified further. Remember that if we want to combine these two parts, we need to add the exponents, right? X squared times x to the 3rd power is equal to x to the 5th power because we added the exponents. 2 plus 3 is equal to 5. So the same is going to occur for n to the 5/2 power and n to the negative 2nd power. So 5/2 plus negative 2 would be 5/2 minus 2. And 2 is 4/2, so 5/2 minus 4/2 is 1/2. And so we would say that this is equal to the sum from n equals 1 to infinity of 1 divided by n to the 1/2 power. Or you could say 1 divided by the square root of n, whatever you prefer. Okay, but now you can see that we have a p-series of 1 divided by n raised to a power of 1/2. And so p is equal to 1/2 for the p-series, and that is less than 1, which means that our p-series diverges. All right, when the value of p is less than 1 or equal to 1, the series diverges, but when it's greater than 1, it converges instead. Okay, but in this case, this p-series diverges. And so now we have our comparison series, and so what we want to do now is look at the limit of the original series divided by that comparison series. So if I clean up my work a little bit, our limit will look like this. We'll have the limit as n approaches infinity of 4n squared plus 5n divided by the square root of 10 plus n to the 5th power. And then we want to divide that by 1 divided by n to the 1/2 power. But since that is a fraction, dividing by that fraction will be the same as multiplying by its reciprocal. So instead of just dividing by 1 divided by n to the 1/2 power, what we can do instead is multiply by the reciprocal, which is n to the 1/2 power divided by 1. All right, so that's going to be a lot easier to work with. And so if we multiply n to the 1/2 power through the numerator, we will need to add the exponents. So n to the 1/2 power times 4 times n squared will be 4 times n to the power of 2 plus 1/2, which is 5/2. So this is equal to the limit as n approaches infinity of 4 times n to the 5/2 power plus 5 times n to the 1/2 power. And so our exponents are 1 and 1/2, and so 1 plus 1/2 is 3/2. So we have n to the 3/2 power. And that will still be divided by the square root of 10 plus n to the power of 5. All right, and so now, if we want to evaluate this limit, can we tell if the highest power of n in the numerator and denominator are equal? Well, in the numerator, we have n to the 5/2 power, and in the denominator, we have the square root of 10 plus n to the 5th power, and so we have n to the 5th power underneath a square root, and so remember what I said earlier, that the square root of n to the 5th power is equal to n to the 5/2 power, right? If the square root is the 1/2 power, 1/2 times 5 is 5/2, and so we have the same highest power in the denominator of 5/2 as we have in the numerator. And so, since those highest powers are equal, this limit as n approaches infinity will just be equal to the coefficients of those terms divided by each other. And so the coefficient of this term is 4, and the coefficient of this term is 1, or the square root of 1, but the square root of 1 is 1, and so this limit will be equal to 4 divided by 1, which is equal to 4. And so this limit is equal to a finite value, and so we can conclude that our original series will diverge just like our comparison series. And so if I clean up my work here, we can conclude that since the comparison series, the sum from n equals 1 to infinity of 1 divided by the square root of n, diverges, that our original series, the sum from n equals 1 to infinity of 4n squared plus 5n divided by the square root of 10 plus n to the 5th power, must also diverge. All right, so that is our final solution to this example using the limit comparison test. We have concluded that this series diverges. All right, here's our next example. We once again want to use the limit comparison test to determine if our series converges or diverges. In this case, our series is the sum from n equals 1 to infinity of arctangent of n divided by n to the power of 1.5. All right, and so the first step of using the limit comparison test is to choose a series to compare to this series. And generally you want that series to be similar to the series you're working with. And so in this case, what type of series that we know the convergence of would be similar to what we have here? Well, we have arctangent of n divided by n to the power of 1.5. If we remove arctangent, then we would just have 1 divided by n to the power of 1.5, and that would be a p-series whose convergence we know. And so let's start with that. Let's use the p-series, where we have the sum from n equals 1 to infinity of 1 divided by n to the power of 1.5. This is a p-series where p is equal to 1.5, and since p is equal to 1.5, which is greater than 1, this p-series converges. All right, if it was less than 1 or equal to 1, then it would diverge, but since p is greater than 1, this p-series converges. Okay, and so now let's use the limit comparison test and see if we can conclude that this series also converges. So we're going to look at the limit as n approaches infinity of arctangent of n divided by n to the power of 1.5, and we're going to be dividing that by 1 divided by n to the power of 1.5. And that will be the same as multiplying by the reciprocal, which is n to the power of 1.5 divided by 1. All right, and so now you can see that n to the power of 1.5 is going to cancel out with itself since it's in the numerator and denominator. And so we're just going to be left with the limit as n approaches infinity of arctangent of n. And so what happens to arctangent of n as n approaches infinity? Well, if you're familiar with the arctangent function, if we're to look at the graph, this would be the x-axis and this is the y-axis. The graph of the arctangent function looks a bit like this. It has two horizontal asymptotes, one at positive pi divided by 2, so that's right here, and then one at negative pi divided by 2, which is down here. And so as x approaches infinity, or in this case, n approaches infinity, but for the sake of this graph, assume that n and x are the same thing. As x approaches infinity, we are getting closer and closer to that y value of pi divided by 2, and so we can conclude that the limit as n approaches infinity of arctangent is pi divided by 2. If we were looking at the limit as n approaches negative infinity, then we would be going to negative pi divided by 2. But since we're approaching positive infinity, we're looking at positive pi divided by 2. All right, so this limit will be equal to pi divided by 2. And that is a finite value, and so we can conclude that this series will converge, just like our comparison series. And so we will write that since our comparison series, the sum from n equals 1 to infinity of 1 divided by n to the power of 1.5, converges, that our original series, the sum from n equals 1 to infinity of arctangent of n divided by n to the power of 1.5, must also converge. Okay, that is the final answer for this example. Let's look at one more example for this video. All right, so here's our last example. We want to use the limit comparison test one more time to determine if our given series converges or diverges. And in this case, we have this series, the sum from n equals 1 to infinity of sine of 1 divided by n. All right, and so this series is a little bit different than what we have been looking at previously. All of our other series involved a rational expression. However, this time we just have sine of 1 divided by n. And so it's not initially clear what type of series we should use to compare to this one in order to use the limit comparison test. And so when you're in a situation like this, I recommend that you just pick a series that you know the convergence of and see if you can use it for the limit comparison test with the series that you want to determine the convergence of. And if the limit as n approaches infinity does not give you a finite result, then you know you need to pick a different series to compare to your original series. So sometimes it might take a little bit of guess and check, but in this case, if we just compare this series to the harmonic series, or the p series, where p is equal to 1, that's just 1 divided by n, we know that since the value of p is equal to 1, that this p series will diverge. And so we have a divergent series that we are going to compare to this series. And so if this also diverges, the limit as n approaches infinity of sine of 1 divided by n divided by 1 divided by n should be equal to a finite value. All right, so if you don't have a rational expression in your series and you're not sure what you should compare to it in order to use the limit comparison test, just try to use a series that you do know the convergence of that somehow relates to the series you've been given. In this case, you see we have sine of 1 divided by n. So that's kind of the motivation of why I chose this series. And you'll see why that actually is going to work when we look at our limit. And so if we write that out, we're going to have the limit as n approaches infinity of sine of 1 divided by n divided by 1 divided by n. And so if you look at this expression as n approaches infinity, in the numerator we have sine of 1 divided by n, and if n is approaching infinity, then this denominator is increasing, or you could say that we have 1 divided by infinity, and that's always going to approach 0. And so in the numerator we have sine of 0, and in the denominator we have 1 divided by n, or 1 divided by infinity, which is also approaching 0. And sine of 0 is equal to 0, so this is equal to 0 divided by 0, which is an indeterminate form for our limit. Specifically, it's an indeterminate form that is compatible with L'Hopital's rule. And so, what we can do to further evaluate this limit is use L'Hopital's rule by taking the derivative of the numerator and denominator and then try to evaluate our limit again. And so if we do that, if we take the derivative of the numerator and denominator separately, we will have that this is equal to the limit as n approaches infinity of the derivative of sine of 1 divided by n. Now that's going to require the chain rule. We'll take the derivative of the outside function first and then multiply by the derivative of the inside function. So first, the derivative of sine is cosine. So we'll have cosine of that same inside function, 1 divided by n, times the derivative of that inside function, 1 divided by n. Now remember, 1 divided by n is the same as n to the negative first power if you move that n to the numerator and make the exponent negative. And so if we use the power rule for derivatives on that expression, we multiply negative 1 down and subtract 1 from the exponent. So we will have negative n to the power of negative 2. And then in the denominator, we are taking the derivative of 1 divided by n, which we just took the derivative of, so we will have negative n to the power of negative 2 again. And now, negative n to the power of negative 2 is in the numerator and denominator, and so those will cancel out, and we're just going to be left with the limit as n approaches infinity of cosine of 1 divided by n. And so as n approaches infinity, 1 divided by n is 1 divided by infinity, and that will become 0, and so this is equal to cosine of 0, which is equal to 1. And so this limit is equal to a finite value, and so we can conclude that this limit will diverge just like our comparison series. And so if I clean up my work here, we can say that since our comparison series, the sum from n equals 1 to infinity of 1 divided by n diverges, then our original series, the sum from n equals 1 to infinity of sine of 1 divided by n, must also diverge. All right, and so that is the final solution to this example. We have determined via the limit comparison test that this series diverges. Okay, and so with that, this is the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.